Hello and welcome back to differential equations. Switch it up a little bit. The lesson today is on regular singular points, and it is the part of all power series solution to differential equations. We observe that we have a method of solving equations when they're constant coefficients, but what happens if each one in front is a function? So if we have ax y double prime plus b of x y prime plus c of x y equals to 0. First of all, what is the regular singular point? So singular point happen when a of x is equal to 0. So if that's the case, then that x is a singular point. What happened? It should be. Yeah, it says live. Health already 140, and you are watching apparently. There's the one person watching. Oh, you're not watching? Then someone else is. Hello. Yeah, we're testing the new computer, so hopefully the sound is going without any crazy stuff happening. So if I take an example of let's say x squared, so Bessel equation, right? X squared y double prime plus xy prime plus x squared minus n squared y equal to 0. Singular point. That's terrible. Singular point would be at x equals to 0. That's an example. Another example would be Legendre equation, where you have 1 minus x squared y double prime minus 2x y prime plus n plus 1 y equal to 0, in which case singular points, we have two now, occur for x equals plus minus 1. So there are two singular points in this case. Now, the great part is that using substitution, we can always shift any singular point that is not at 0. So we can only theoretically work with the cases where singular points are x equal to 0. And whatever time we get the equation, like Legendre equation, where it's not a 0, we can use a simple transformation to shift. So in this case, if you say that t is equal to x minus 1, right? If this is the case, then the singular point now is t equals to 0 and t equals to negative 2. But we have the t equals to 0, which is the one that we are trying to learn about. And that can be, right, so you would use this, and you would use derivatives, obviously, to plug everything in. So y would be now a function of t, which is shifted, and all of that kind of stuff. Not a big deal. Use a little bit of chain rule. So we are focusing primarily on these cases where singular points are at 0. Now, what types do we have? We have two types. We have, first of all, why are we doing this? Because we have to figure out a different way of solving differential equations. Power series Cn x to the n doesn't work. We have to have a different type of power series in this case. So for singular point at x equals 0, power series approach, which is set y equal to summation 0 to infinity cn x to the n, does not work. We have to come up with something else, and we will. It will method of Frobenius, which is what we are learning now, is going to introduce more x times x to the exponent in front of the summation, and then there will be just more of shifting counters and things like that coming up. So what we did the last time is we said that if you're starting with a of x y double prime plus b of x times y prime plus c of x times y equals to 0, you can divide through by a. But see, the trick is that, remember, the singular point is making the a 0, right? Which means that all of the denominators will be 0. Right? Right. So if I am to write y double prime plus b of x over a of x, y prime plus c of x over a of x, y equals to 0, and we know that this a of x is going to 0, we can still call this p of x, but we know the denominator goes to 0, in which case the entire term over there could possibly go to infinity. And then we do our classifications. So call it y prime, y double prime plus p of x y prime plus q of xy equals to 0. No coughing. So what am I looking for over here? Well, I can define, so we can actually put the definition there. This p of x as lower case p of x, which is some kind of polynomial. So then this is the lowercase p of x divided by x y prime plus lower q of x divided by x squared y equal to 0. And in order to get our classification, we will say that if p of x and q of x are analytic, which means they are polynomials, say, well behaved in terms of they have derivatives, continuous, and all that kind of stuff, then we have the regular singular point. If that's not the case, we have the other one, which is irregular point. So this is the definition. I use my colors here. So the singular point x equals 0 is a regular singular point if the functions lowercase p of x and lowercase q of x are analytic. Otherwise, it is irregular. I will have like 5,000 different examples to kind of classify these points. And then the method of Forbini is to actually solve differential equations using this. So again, this is not replacing what we learned last class or making it better or anything like that. This is dealing with the situations where you are trying to expand around 0, let's say, because that's where your initial condition is, and then you have a singularity at 0, right? So can it be a condition? It's singularity and condition, but I said in the neighborhood of it, right, close to. All right, so what do we have? Basic example just to show off the definition. Y double prime plus 1 over x y prime plus x squared minus n squared divided by x squared y equals to 0. So in this case, and I'll write it in blood, p of x is equal to 1 and q of x is equal to x squared minus n squared. So both of these are polynomials. Both of these are behaving nicely. So at a equal to 0, we have what we call a singular point. So, or regular singular point. Both polynomials which says that x equals 0 is regular singular points. So you should be able to, but make sure it's divided by x and x squared, right? That's how you can fool. So if this was, let's say, just, if this term here was just, let's say, x cubed y prime, you would have to rewrite it as x to the 4y prime over x, right? So you have to be careful about those kind of things. And then you look the whole problem. So let's consider a different example. X squared 1 plus x y double prime plus x 4 minus x squared y prime plus 2 plus 3x y equal to 0. So the first order of business is to see that we have two singular points. One is at 0 and one is at -1. Do we all see that? Singular points happen when ax is equal to 0, right? So singular points are x squared 1 plus x equal to 0, from where x is equal to 0, x equals -1. So we have two singular points here. Now, in order for us to say whether they are regular or irregular, all we need to do is to divide by this and then check what's happening with limits. So y double prime is equal y double prime plus x 4 minus x squared divided by x squared 1 plus x y prime plus 2 plus 3x divided by x squared 1 plus x y equals to 0. Now you hopefully see that these guys cancel, right? So we do have over x and we do have over x squared. So now what is the p of x? Remember that little p of x is equal xpx, right? That was from the last time. So I do have this x at the bottom right here, right? So if you think about that, the big p of x is equal to lower p of x over x, you can see, and that's what you have. You can see that the lowercase p of x is given as everything else except that x. So 4 minus x squared 1 plus x, and that's lowercase p of x. And similarly, we have for q, so q of x is going to be 2 plus 3x divided by 1 plus x. So what's happening for x equals to 0? For x equals to 0, now we see at x equals 0, we have okay behavior, right? At x equal to 0, both expressions are polynomials, which means analytic, which by the definition over there tells us that we have regular singular point at x equals 0. And we were looking for the regular part. All right, so that's the first part of the lecture where you just learned to differentiate between regular and irregular singular points. Now we are going to use that knowledge in a method of Frobenius because this works for regular singular points. Is the stream okay? It's kind of yellowish, but it works, I guess. Testing the new computer, so I hope there is sound. There is sound? Okay, so I hope it's not clipping. So what is this part of method of Frobenius now to use what we know solve differential equations using power series? As I said before, when you have a singular point, the method from previous lecture, which was 3.2, doesn't work. So you can't say y equals the summation of Cn x to the n. Now it's modified, and that modification calls for y equals x to the r summation 0 to infinity or Cn x to the n. So that's the new piece for the solution. So we are assuming this one. Well, so yeah, we're assuming this one. What I want to write here is summation Cn x to the n. I was supposed to put this n in exponent. I'm so lost. So n plus r. 0 to infinity. And then y prime is going to be counter shifts by 1. And we have n plus r cn x to the n plus r minus 1, whatever those values are. And then you can shift if you have to. And y double prime, not sure why I put 3 of these. And y double prime is equal to summation 2 to infinity of n plus r minus 1, n plus r cn, and then x to the n plus r minus 2. So this is what you are subbing in your equation. So now what do we do with these things? You have what you're assuming is the solution. You have the y prime, y double prime. You feed them. But look, you don't have your r's, right? We have to compute r every time. And when you compute the r, you plug in the r, and then you plug all of these into the differential equation, and you crank the same stuff we did earlier. But as you can see, to start off, this is your 3.2 when you're plugging in the power series, and your 3.3 has the extra piece. Now, this exponent here, the r exponent, is not going to be integer exponent. It's going to be some kind of fraction exponent. Because if it was an integer exponent, then this would actually work in 3.2. So that r is going to take us away from what we are used to from the previous section, right? And this method takes more time to solve because you have to also grind and find r. So I'll just write here, need to find r. I'll put r's, the multiple. Then plug all in ODE, right, ordinary differential equation, and just compute. So let's take a look at the example. We might have time to finish the example. and then I guess, well, I know, it's amazing, right? Differential equations, every problem now, it takes like a year. And wait for the Laplace next class, right? We're going to do the, are we supposed to have an exam or no? We covered what, chapters? Finished chapter 2, so half of chapter 2, chapter 3. Yeah, I finished Laplace, right? I have some kind of exam. Yeah, because we have 3 exams. And then after Laplace, I think we have another 3 sections to go. We have numerical, we have systems, and nonlinear. So 3, that would be good for another exam, which is exam 3, and then final for everything. So it's a good spread. Final for this class? Yeah, it's going to be hell on earth. But good thing is you're preparing for it, you know, every day now, so it won't be a problem at all. Yeah, just don't forget about reading days. It's like that's not when you look at this stuff.
Now is reading day.
Your reading day is every day prior to reading day. Take the day off on the reading day when you're in this class. All right, so here is the example, and let's take a look at this. So we know what we're supposed to do, right? Divide by a of x. Well, first of all, where are the points, right, at x equals 0 and -1, right? So we are going to divide everywhere by x squared, so I'm getting y double prime is equal to 3/2 1 plus x cubed divided by x squared 1 plus x. Why am I constantly putting equal sign? I should be hitting the shift. There we go. Y prime minus, and I hope you see that 1 minus x squared is 1 minus x, 1 plus x, so one of them cancels with 1 plus x that I'm dividing by. So that's going to be 1 plus x, no, 1 plus x canceled, 1 minus x remains, divided by 2x squared, y equal to 0. So, did I do this right? Yep. And now we see that we have, this was supposed to be x, not x squared. So we see that we have a single x here and the x squared there, right? So what do? Let me just write it one more time. Again, equal, holy nightmare, plus 3/2. 1 plus x will cancel, so I have 1 plus x squared on top divided by x, y prime, plus -1/2 over here as a coefficient of 1 minus x divided by just x squared equal to 0. So all of that stuff cancel, right? And we see what we have here. Now remember, we are dealing with the singular point at x equals to 0, which will just leave us with numbers 3/2 and 1, -1 over half, -1 over 2. So what do I have as a little P0? 3/2, and the Q0 is -1/2. So plug all of that stuff in the differential equation. R minus 1 plus 3/2 R minus 1/2 and equal to 0, and solve it for R. So what do I get? R squared minus R plus 3/2 R minus 1/2 equal to 0. Multiply everywhere by 2 to kill fractions. 2R squared minus 2R plus 3R minus 1 equal to 0. So that's when I multiply the whole thing by 2. And finally I have 2R squared plus R minus 1 equal to 0. When you factor, you get your R's. So I factor this now as 2R minus 1 and R plus 1, right? Is that good? So 2R squared, that's 2R minus a single R negative. Yep, boss. So R is equal to 1/2 and R is equal to 1. R is equal to -1. For those of you who are not paying attention, which is everyone. So what are the solutions? What do I use to crank the series solution with? Y1 is equal to summation, x to a half times the summation 0 to infinity of Cn x to the n, and y2 is equal to x to the -1, we can put 1 over x, summation 0 to infinity Cn x to the n. Now observe when these values get inside, right, over here, that's going to be n plus a half. mentioned before, let me just find where the substitutions are. That's that n plus a half. So that r you calculated. And this is now where the rest of the grind begins. First derivative, second derivative, plug everything in, and spend another hour solving. So we have technically we have a superposition. Ooh, crucial mistake. Crucial mistake. Look at this. I put Cn for both. They're not the same value. So let's swap them with I don't know, An, Bn. Now, the overall solution is y equals y1 plus y2. We know that by superposition, so technically that's these two series put together. So an x to the n plus 1 half, and then plus the series of 0 to infinity bn x to the n minus 1. And take the first derivative, take the second derivative, plug all of it in, and in about an hour, 2 hours, you guys, it's good. Like, this is a good problem for the final to be the only problem on the final. Because we did all of this preliminary work, and now it's time for everything to actually plug in. So first derivative, second derivative, plug them where they belong in the equation, and then keep grinding until you get the stuff. So it's a lot of work. It's a lot of writing. And that's the method. So question is whether you're going to sit there for 2 hours and crank the problem all the way to the end. But this is the new part. So this part here is the new part where you look at the singular point and find the values P0, Q0, which will give you these R's. And those R's are in front of the, so this is the piece that is new, and you are looking, so to solve the differential equation, now you have to have that piece there. Now if you have multiple ones, you will have to do the superposition of both solutions because they're linearly independent. So their superposition is the overall equation, overall solution to the differential equation. I don't know why, but there are 35 problems for you to practice. So that's literally, if each one takes about an hour, it's 35 hours of solid homework assignment for this one section. And then you paid, what, $10 per hour, so, you know, it works out to be $350 out of one homework. Good. All right, so that's it for today. In terms of this one, we'll talk about, let's talk about exam, next one is chapter 4, Laplace. So we will start, well, we can't start now, the class ends in five minutes. But next class we will talk about Laplace, but I want to tell you that in order for you to perform in this class, you need to, in this chapter on Laplace, guys, please review integration by parts, okay? So you have the Calculus 2 notebooks. Hopefully, if not, look for my videos on my channel. For 7.2 in Calculus 2, 7.2 integration by parts, because that one will be essential for you to solve integrals. There will be a lot of integration. Review integration of e to the negative x. How does that behave? So take a look at the problem. I don't know, I'll put this over here at the end as a preparation for the next class. So try to integrate x squared e to the minus x dx. So integrate something like that in preparation. So over the weekend, look at integration by parts, particularly solve this problem to make sure that 100% understand how to do this so that you can dive right into Laplace and actually understand everything. And by far, Laplace is one of the most used techniques, right, for engineers, other than Wolfram Alpha Mathematica and so on. Okay. Let me say bye to the stream first. Bye, stream.